Okay, we're going to look at Euler's method. Pronounced Euler, also some people say Euler, but yeah, the same guy that figured out the number E. Okay, and this method is going to be a numerical approach to approximating a particular solution of a differential equation. So a slope field was a graphical approach. So when you did like the slope fields, it was kind of showing you, hey, we had all these different ones, and it kind of gave you a family of functions. Which one is it? And you can see the picture of the graph. You can see what the shape was on the slope field. Right? Euler's method is going to give you a numerical approach to getting it. And what it does is connect points to make short line segments. So something like this. Now, if I went from this point to this point, this point, this point, this point. I mean, you kind of picture a curve rolling through there. Now, obviously, this is not going to be perfect because the points are really far apart, okay? So what Euler's method is really doing is it's taking points very, very close together. So in other words, something like this, where I had, hey, I've got a point here, then a point there, and a point there, and I just keep going. And you kind of get the idea. Picture these dots now being connected. You can see it make the curve. Well, theoretically, those dots are still really far apart. All right, so the question comes in, well, how many points do we need in order to get the full, complete picture of the curve? Well, we need an infinite amount of points, and that would give us our particular solution. Particular solution just means the particular curve we're talking about, right? That differential equation, give us that original one. Well, we're not going to have to find an infinite number of points. What we're going to look at is finding a finite number of points, so we kind of get the gist of what's going on. And then the theoretical part would be we do understand that it's going to take an infinite amount of them, which is something that we can do nowadays when it comes to a computer. When you set up a program to just go through and crunch all those values, and it's going to generate 50 million points or something like that. But we're going to just take a look at going from one point to another to slowly generate this graph. So let's investigate this. Here's what we're going to do. We're going to have a starting point, and we're going to go at a particular slope from this starting point to the next point. Then we're going to go at a particular slope from this point to the next point, and we keep developing it through. Now, what to remember is they're line segments. I mean, I made these a little bit bigger for viewing, but they're tiny little line segments, even smaller than that. Okay. So where this method comes from is from the equation of a line. So how do we find an equation of a line? Well, we start with y minus y1 is mx minus x1. This is our old, hey, if I know a point and a slope, I can get the equation of a line. Nothing's new on that. And what looks a little different is when we set up Euler's method, it looks different, but it's still going to be this basic thing. So kind of watch what happens here. We can rewrite this as y minus y1 equals m times delta x, the change in x. And the reason I'm saying change in x or delta x from whatever this x value is to whatever that one is, that would be that change in x, so on and so forth, right, for that piece. We can now rewrite this as y minus y1 equals m times h. Right? And h is what we call a step value. Right? So h equals the step value. And it just means how far are we between x's. So if I said that this point right here was 1 something, and this point right here was 3 something, then the step value would be 2. That'd be the difference in the x's. But the step value is going to be consistent throughout. So this would be 5 something. So 2 units between the x values. So it's that consistent amount because we're keeping these points sufficiently close. Now, let's think if we got decimals. So the step value here would be 2. What if I change this x value to 1.2 and this x value to 1.4? Now the step value would be 0.2 units. So in other words, those points are getting closer together, maybe not quite that close, but they're definitely getting closer together. So in order to get an accurate graph, we need the step value to be infinitely small and an infinite number of points. And that's going to make them very close together and create that full graph. So h is that step value. That shows up in my formula, but that's really the change in x, which was x minus x1, developing that piece. Slope. Typically, we will see slope written as, so you go y minus y1, f prime of xy, h. Now, this just means the derivative of whatever function I'm talking about. Developing through the way that it's presented in your textbook, right? The way that we see that general form, and trying to relate it back to what we've done. Okay, change in x, you just call it h, how far between the x's. F prime, wait, well, that's the slope. Places m. Slope of the tangent line. So we're basically taking the slope of the tangent line to get to the next point, the slope of the tangent line to get to the next point, the slope of the tangent line to get to that next point. That's what we're looking for. That slope we're going to lead from. Then I would have y equals y plus f prime of x, y, h. There is my formula for Euler's method, or Euler's method. Sure pronounced that right, Euler's method. It doesn't matter what the subscripts are. Like if I move this over, yeah, that's y1, okay? But what's going to happen to us is we're going to have an initial point, all right? And so typically, this would be the initial point 0. So I think that was my 1, whatever my initial y is. So the y I'm leaving plus the slope times the step value. So if this point was 1, 2, then that would be a 2. Okay? And we're going to kind of see how this develops with the different points. But this is the formula. This is the formula they present you with, the standard form of Euler's method. But I want you to understand it's really from this guy right here. Now this is something that we have found, equation of lines, in this course already. There's nothing new about that. So we've used this guy. That's something we should remember. So if we can relate this to this, it'll help us remember the formula. Where's the slope come from? Derivative. What's the h? Well, the change in x. Where did this guy come from? Move this y to the other side. That's all we did for solving that piece. And it'll develop our part. All right, let's look at an example here. So let's say I have the differential equation. Y prime equals, and I'll do negative 2x plus y. So there's my differential. And what I'm wanting to find is the original. All right. So I'm going to say initial value. So this is a point I know on the graph. Y of 0 equals 3. And step size, h equals 0.1. Okay. So what we're going to do is we're going to start at 0.3, and we're going to move in this short step size 0.1 and find the next y values that are going to occur, and that will give us our point. So we're just going to go through a few steps of this. Here's what I like to do when I'm finding Euler's method. I like to always put the point I'm starting with, 0.3. That's where I'm starting this. And then I go through the step size. So we're going to go 0.1 something, 0.2 something, and we'll 0.3 something, and we'll stop there. So we'll find 4 points using Euler's method. We've already got one of them at 0.3. All right, so we're going to be starting at 0.3. Picture a graph. Hey, we're right here, 0.3. And I want to know where 0.1, what y value am I at? And it's going to slowly develop that graph. All That's what I'm working with. So my new y value. So this is what I'm going to use. This refers to my new y. This is my previous y. I mean, in the beginning, it's going to be the original y because it's the only one I have. But then subsequently, it's going to be the ones right before it. Okay. All right, so my new y. Y will equal my previous y, 3, plus the slope at this point. So remember, y prime, there's my differential equation. This represents the slope. So if I put 0 in for x, negative 2 times 0 is 0, plus 3 is 3. So there's my slope times 0.1, because that's the change in x. There's that change in x. There's that h now, that's step size. We're calling that change in x. So this would give me 3.3. Calculate that out. So there is my new y value. So I've moved from 0.3 to now 0.1, 3.3. So let's see again graphically. I guess I shouldn't have erased this. All right, here's 0.3. That'd be 4. That'd be 1. So 0.1, 3.3. They're going to be really close, like something like right there. All right, kind of tough to draw, but they're really close together. So now I'm going to go for my next point. My new y equals the y I'm coming from, 3.3, plus the slope here. So I'm going to do negative 2 times 0.1 plus 3.3. So when I leave this point, I am now at a slope of 3.1 times my step size, 0.1. So again, here's my x and y value. Going in, that will give me my slope at this point, which will calculate to 3.1, then times my step size. So now my new y value is 3.61. There's my new y value, 3.61. So I went a little further on the x, 0.2, and I know this graph's really close together. I went about 3.6. I'm climbing up right there. For my last one, y equals 3.61, my previous, the one I'm leaving, plus, all right, now we're going to put x and y in here so I can get my slope. So that's negative 2 times 0.2 plus 3.61. That gives me a 3.21 slope times that step value of 0.1. So again, substituting x and y is going to give me my slope times that 0.1 step value. If I calculate this out, .931. Right. And make sure, pause the video, see where these values are coming from, rewind if you need to, whatever's going to help us here. All right? But there's my new y value, 3.931. And I'm going to stop there because I didn't have another x value down there. So I went through 3 steps of Euler's method, found 4 points. So now this 0.3 is like right up here, and I'm just slowly developing that graph. Is that near enough points to get me a sketch? No, not even close. So here comes that theoretical part again. How many points do I need? I need an infinite number of points. This curve is going to be a very lengthy curve. Domain's going to be quite big. That's not much of a graph there. But we're trying to just get the idea. This was that numerical method where I'm slowly going through and getting the next point in line at this step size. I mean, I can increase the step size, but I'm not going to end up with a smooth curve. Remember, for the curve to be smooth, the points have to be really close together. Right? And so we can usually keep the step size low, but you get the general idea of what's going on. So then we can understand that theoretical part of, well, this needs to be smaller, maybe not 0.1, maybe 0.01, and then I need an infinite number of points to develop this full curve for that piece. So it gives you kind of an idea there. Let's look at another one here. let's give you a differential of, let's say y prime equals 0.2x 2 minus y, and we'll say initial value 0.9, and with h of 0.2. Now, I've got my initial value there at a 0, but it doesn't matter where you start. I just started at the 0. So if I had started, let's say this started at 1.3, well, then that'd be 1.1, something like that. So let's kind of look at that. Change this from 0, make it something different. Let's say you got an initial point of 1.9. Initial point of 1.9, and let's go through a few steps here, because I don't want you thinking we always start at 0. So again, the first thing I'm going to do is write down my initial point, 1.9. And then I'm going to write down how many I'm asked for. So let's say we're going to go 3 again. 1.2 something, 1.4 something, 1.6. You'll never be asked, or I'm not going to ask you anyway, to do 10, 20, 30 points. In my opinion, if you could do 2, 3, 4, 5, you could do 50 if you had to, because it's the same process over and over. And typically, even on a test, and even say an AP test, they don't ask you to do more than a few, because again, if you can get a few done, you could do many. So notice 0.2 took my x value. So then I've got 1.2, 1.4, 1.6 because my step size was 0.2. Now I'm going to go get each of my new y values. So my first new y value, y equals my original y value, or the previous y value, the one I'm coming from, 9, plus. Now I'm going to put 1 and 9 into my differential. So I'd have 0.2 times 1 times 2 minus 9. So let's see, that would be 0.2 times, and 2 minus 9 is negative 7. So negative 1.4. And then my delta x, or my h, is that 0.2. There's my step size. We're going to have a negative slope. That's fine. Okay. If I calculate this, my new one would be 6.2. Here's that new y value, 6.2. I go for my next one. Previous y. Now I'm coming from this point. So I got y equals 6.2 plus. We go get my slope. And I still know my h value is 0.2, so I'm substituting now 1.2 for x, 6.2 for y. Let's see, 2 minus 6.2. I get negative 1.008. Here's my slope. I get 5.9984. $5.9984. And I knew I had something wrong there. This is where the video kind of fails us. Let me go back and fix this. Some of you probably already caught it. If you didn't, we'll get you straightened out here. But I thought I calculated something wrong. If I did the negative 1.4 times 0.2 plus 9, I got 8.72. I knew something was off there on that piece. Hopefully you caught that before I did. Now I'm going to be moving from 8.72. Sorry about that mistake. So now I'm putting this in for x, y. So I'd have 0.2 times 8.72 times 0.2 times 1.2 times 2 minus 8.72. So there's my slope, negative 1.6128. And I get a long decimal here, 8.39744, so I'm just going to go 8.40, rounding off. Keep it at 2 decimal places. All right. So sorry about that mistake, but the one thing I did, can I catch you back up? I just put this in my calculator wrong, and so I had a different value, so now it's really 8.72. There's my new y value. Previous y value, where I'm coming from. Slope, when I put those two in, negative 1.6128. Here's still my same step size. Here's my new y value, 8.40. Now I'm coming from that y value. Okay. I know this is going to be 0.2. I got to figure out this slope. So I'm putting 1.4, substituting 1.4 for x, 8.40 for y. I've got negative 1.792, my slope. So continue this. That gives me a total of I'll stay at 2 decimal places, 8.04. So again, kind of picture the graph being made. I'm starting at the 0.19. I go 0.2 units to the right, and I come down about 0.28. I go 0.2 more units to the right, and I come down another 0.32. I go another 0.2 units to the right, and I come down, 0.36. So slowly moving along, moving in the downward direction this time as far as getting those values. But that completes 3 steps, creating 4 points using Euler's method. So again, how many points do we need? We need an infinite number. How close do they need to be together? Infinitely close. But this has given us a general idea of how the graph can be created 1 point at a time. Yeah, it would take forever, but it's creating it 1 point at a time, and we can see how it's just slowly moving along decimal-wise.